Hello everyone, and welcome to Math 131A, Week 2, Lecture 1. We begin by recalling the material covered in the previous lecture. We have discussed the difference of powers formula, which provides a way to represent a difference of the form a to the power n minus b to the power n, where a and b are arbitrary real numbers, and n is an arbitrary natural number greater or equal than 2. Secondly, we have deduced Bernoulli's inequality, which said that for every x a real number and every natural number n, if 1 plus x is positive, then taking the nth power of this expression, 1 plus x to the power n, is greater or equal than 1 plus n times x. And finally, we have used these two results to demonstrate that every real number has nth roots for all natural numbers n. In this, we were able to argue how to define the power operation, so the operation of the form x to the power y for x and y arbitrary real numbers. In today's lecture, we are going to cover the following topics. We begin by introducing new notation for products of sequences of real numbers, the so-called pi notation, which is analogous to our sigma notation for sums of sequences of real numbers. 2. We discuss two kinds of taking the average of a finite list of real numbers. So, namely, we will define the arithmetic mean and we will define the geometric mean. These are two ways to average a sequence of real numbers with respect to the summation or with respect to the product in the corresponding cases. And we will establish a very important inequality, the so-called arithmetic and geometric mean inequality, which is abbreviated as the Agm inequality, which provides a relation between these two kinds of means, the arithmetic mean and the geometric mean. And finally, 4, after establishing this inequality, we will discuss two symbols, plus infinity and minus infinity, how to introduce them in order to extend the real line to include these two new symbols, and how they're used to simplify notation when talking about intervals, bounds, etc. So the first topic is products. Just as in the case of summation, we're going to use the following notation. Suppose that we're given two integers m and n, such that m is less or equal than n. And suppose that we're given real numbers, a starting with the index m, then a m plus 1, etc., up to an. So these are arbitrary real numbers, indexed by the integers in the corresponding interval between m and n. Then we will denote the finite product of these integers, am through an, is denoted using the Greek letter pi, where we have to specify the index varying from, let's say, m up to n, and here we have the element ak, where k corresponds to the index running through this list, so the index k, and this notation simply represents the product am times am plus 1 times etc. times an. So it's a long product, the product of all these numbers on the list, which is the same thing as the product of ak, where k varies through the list from starting with m and ending with n. And just as before, this index k is absolutely unimportant, so we could use any other letter or expression for indexing. So as before, we have that the product of the numbers ak starting with k equals to m and up to n is the same thing as the product over, let's say, l starting with m up to n. al is the same thing as the product over all j starting with m up to n, aj, etc. So we can use different expressions for the index of the corresponding product. Another thing we can do with a sequence of real numbers is to try to find its average. To more specifically assume we're given real numbers listed as a1 up to an. First we define its arithmetic mean. So the arithmetic mean of the sequence a1 through an is going to be the expression a1 plus a2 plus etc. plus an divided by the total number of the reals in this list, which is n. Equivalently, we can write it using the summation notation. So this is 1 over n times the sum over k from 1 to n of the numbers ak. Analogously, if we assume that each ai is positive, we can define the geometric mean of a1 through an to be the product a1 times a2 times etc. times an taken to the power 1 over n. And here we are using the existence of nth roots of real numbers established in the previous lecture. And using our newly introduced product notation, we can write it equivalently as the product over all k from 1 up to n ak, and we take this expression to the power 1 over n. So in each of these two cases, the idea is to look at this list of real numbers that were given and try to take a real number which is average with respect to this sequence. In the first case, we do it with respect to the addition operation, and in the second case, we do it with respect to the multiplication operation. This raises a natural question: how are these two quantities connected? And the answer to this question is given by the inequality, the so-called arithmetic and geometric mean inequality, which we will in the future call for brevity the Agm inequality. It guarantees that the geometric mean is always less than or equal to the arithmetic mean, and moreover, the only way these two means can be equal is if all of the numbers ai on the list are equal. So let's record this precisely. The Agm inequality states that for every natural number n greater or equal than 2 and any positive real numbers a1 through an, we have that the geometric mean a1 times a2 etc. times an taken to the power 1 over n is less or equal than the arithmetic mean, so a1 plus a2 etc. plus an divided by n, where the equality holds if and only if we have that a1 is equal to a2 is equal to an. So precisely in the case when all of these numbers are equal, if at least two of them are not equal, then we get a strict inequality instead of less or equal here. Our next task is to prove this inequality. We're going to use a variant of the principle of induction, which is attributed to Cauchy. So for n greater or equal than 2, we let P of n be the following assertion. For all positive a1 through an real numbers, we have that a1 times a2 etc. times an is less or equal than a1 plus a2 etc. plus an divided by n to the power n, with equality if and only if we have that all of these numbers a1 through an are equal. Okay, so this is our statement P of n. Our task is to show that P of n holds for all n. Note that we have written a slightly different inequality here as opposed to the one stated in the theorem. However, it's easy to see that these two inequalities are equivalent, simply because we use the properties of the nth power with respect to the inequality. So it's the power inequality where we take nth power of both sides here, and this is how we arrive at this inequality, and it's equivalent to it. Okay, so it would be enough to show that this inequality holds. So now our task is to establish that P of n holds for all natural numbers n. Let's first look at the simple case P2. In this case, our inequality is simply the inequality a1 times a2 is less or equal than a1 plus a2 divided by 2 squared. Yeah. So we just substitute n equals to 2 in the corresponding inequality. Let's rearrange this inequality in an equivalent way. The right-hand side can be expressed as a1 over 2 plus a2 over 2 square. Now, just viewing it as a product, it's the same thing as a1 over 2 plus a2 over 2 multiplied by a1 over 2 plus a2 over 2. This is the same thing as a1 over 2 squared plus 2 a1 over 2 multiplied by a2 over 2 plus a2 over 2 squared. And for the left hand side, we can write equivalently that this is 4 times a1 over 2 times a2 over 2. Okay? Now let's look at the middle summand on the right hand side and the left hand side. Moving the this everything to the right hand side, we thus get that this inequality is equivalent to 0 is less or equal than a1 over 2 square minus 2 times a1 over 2, a2 over 2, plus a2 over 2 square. But now this expression is familiar with respect to the formula for the difference of powers. Okay, so this is equal to a1 over 2 minus a2 over 2 squared. In other words, our inequality can be rewritten as 0 is less or equal than a1 over 2 minus a2 over 2 squared. But we know that the square of any real number is non-negative. So in particular of the real number a1 over 2 minus a2 over 2. Okay, so then this means that this inequality always holds as the square of any real number is non-negative, and we get the equality here if and only if a1 over 2 is equal to a2 over 2, which is the same thing as a1 is equal to a2. Okay, so we get that the equality holds only in the case that a1 is equal to a2. And so looking back at the definition of the property Pn, this demonstrates that P2 holds. Why did we start with P2 instead of P1? Because in this situation, instead of using the usual principle of induction, it is more convenient to use a different principle, the so-called Cauchy principle of induction, which allows to establish that the property holds for all natural numbers by establishing certain implications between this property P of n for different values of n. So more precisely, in this case of the Cauchy principle of induction, we want to prove two statements. So assume that the following two conditions hold. A, for n greater or equal than 3, if P of n holds, then P of n minus 1 also holds. Okay, so note that in this case we are going from a bigger number n to a smaller number n minus 1. And this makes sense because n is guaranteed to be greater or equal than 3. So n minus 1 is at least 2. This is the A part. And the B part, for n greater or equal than 2, if P of n holds, then P of 2n, so 2 times n, holds. Okay, so assume these two properties, then the conclusion is that P of n is true for all natural numbers n. This is an interesting principle. This is an interesting variant of the principle of induction and can be deduced from the usual principle of induction, as you will see in a homework problem. But for now, we're going to assume that the Cauchy principle of induction holds, and we're going to apply it to our situation. So we're going to prove that conditions A and B hold for the specific property P of n that we're considering here. For the A part, we need to show that for all natural numbers n greater or equal than 3, if P of n holds, then P of n minus 1 also holds. So let's assume that we're given natural numbers a1 up to an minus 1, all positive. So these numbers are given to us, but now we also define an additional real number, which we're going to call an plus 1, and we're going to define it as follows. So we take the sum over all k from 1 to n minus 1, ak divided by n minus 1. The purpose of defining this additional number is that we are trying to use the principle Pn holds. So we need n real numbers to be able to apply it, right? And so we start with n minus 1 real numbers, and we define an extra real number an in terms of the given ones. Now our task is to estimate the product of these numbers. So let's write it a1 times a2, etc., times an minus 1 times an, this newly defined real number. Now we can estimate it from above using the fact that p of n holds as the arithmetic mean, so a1 plus a2 plus etc. up to an minus 1 plus an divided by n and take to the power n. So this is precisely the fact that p of n holds. And with equality, if and only if all of these numbers are equal. So a1 is equal to a2, etc. is equal to an minus 1 equal to an. And note that this happens if and only if a1 is equal to a2, etc. is equal to an minus 1. Because the condition of being equal to an is going to follow automatically, simply because if we look at how an is defined, if all of the ak for k from 1 up to n minus 1 are equal, then the value of an is going to be the sum of n minus 1 equal elements divided by n minus 1, so the value of the sum is also going to be equal to each of those elements. So then we get that the equality of all n of them is equivalent to the equality of just the first n minus 1 elements on this list. Okay, so here we apply the property Pn. Now consider the sum of the first n minus 1 elements in the expression on the right hand side. This is equal to n minus 1 times an. Simply because the way we define an is the sum over the n minus 1 of the ak's divided by n minus 1. So multiplying by n minus 1, we get precisely the sum of the first n minus 1 elements. Okay, so let's rewrite it as equal to the expression n minus 1 times an plus an divided by n, and all of this to the power n. But this expression simplifies to n times an divided by n to the power n, which is equal simply to an to the power n. So let's look at the two sides of this inequality. On the left hand side we have the product of a1 up to an, and on the right hand side we have an to the power n. Now our task, in order to prove the condition p of n minus 1 holds, we have to estimate the product of a1 up to an minus 1 from above. So then we simply divide all parts of this inequality by an, and we arrive at a1 times etc. times an minus 1 is less or equal than an to the power n minus 1. And finally, remembering how an is defined, this is equal to the sum a1 plus a2, etc., plus an minus 1 divided by n minus 1 and taken to the power n minus 1. So comparing the left-hand side of this inequality and the right-hand side, we see precisely that this is the condition p of n minus 1. So we conclude that p of n minus 1 holds. And this proves the condition A from the Cauchy principle of induction. So we have so far demonstrated that P of 2 holds, and we have demonstrated that A holds. So the remaining part is to show that B holds. Recall that B says that for n greater or equal to a natural number, if P of n holds, then P of 2n also holds. So let's show this implication. So we start with natural numbers a1 up to an plus 1 up to a2n, and we assume that all of these are 2n positive real numbers. So this corresponds to P of 2n, right? So our task is to estimate the product of these 2n real numbers from above. So let's look again at this product. So we have the product over all ak from k equals to 1 up to k equals to 2n. We can split this product into two parts. So we can first look at the product of the first n numbers. So this is the product over all k from 1 to n of ak multiplied by the product of the remaining n numbers. So we have the product over all k varying from n plus 1 up to 2n ak. Applying the condition Pn, which we assume holds for each of these two products, we can estimate each of these two products from above by corresponding expression. Hence, the product can also be estimated from above using the basic properties of powers. So we have that this is less or equal than the sum, so the arithmetic mean over all k from 1 to n ak over n to the power n multiplied by the sum over all k from n plus 1 up to 2n of ak divided by n to the power n. And again, by Pn we have that the equality holds if and only if we have that the numbers from a1 to an are all equal and the numbers an plus 1 up to a2n are all equal. This is a product of two nth powers, which is the same thing at the nth power of the corresponding product of these two multiples. So we can rewrite this as the product of the first sum from k equals 1 to n ak over n multiplied by the second sum, so k varies from n plus 1 up to 2n ak divided by n, and we take the product to the nth power. So this is just the basic properties of powers and multiplication. Now this can be estimated from above by the following expression. So we have the sum over all k from 1 up to 2n ak over n divided by 2 to the power 2 to the power n. How did we arrive at this estimate? Well, we consider the first expression in brackets and the second expression as brackets as two real numbers, which are just given by evaluating the corresponding sums. So we can call this real number a1, and we can denote this real number as a2. And now, to obtain the expression on the right hand side, this can be rewritten as a1 plus a2 divided by 2 square. Okay? And we know that a1 times a2 is less or equal than a1 plus a2 divided by 2 square by p of 2 applied with respect to the capital A1 and the capital A2. Yeah. So this is just an application of P2, this inequality in red. But now what happens in the original inequality that we are looking at, we're just taking each part of the red inequality to the nth power. And so we know that by the power inequality that taking nth powers preserves the inequality. So this is how we arrive at this inequality here. And moreover, as a part of the assertion P2, we have equality if and only if the sum over all k from 1 to n, ak divided by n, is equal to the sum over all k from n plus 1 up to 2n ak divided by n, just because in the condition P2 we get equality if both of these two numbers are equal. But this happens if and only if a1 is equal to a2, etc., is equal to a2n. Since from earlier we know that either of these two equalities can be obtained only in the case that the first n numbers, all of them are pairwise equal, or the second n numbers, all of them are pairwise equal. And finally, this expression can be rewritten as the sum over all k from 1 up to 2n ak divided by 2n, just looking at this 2 and this n here, putting everything into the denominator, so divided by 2n and taken to the power 2n. So here we just, a power of a power is just the sum of the powers, right? So we obtain this equality. Now what does it give us? So it gives us an upper estimate on this product here. So the product of the ak's, starting with k equals to 1 up to 2n. And the upper bound that we have obtained is of this form. And so note that this is precisely the arithmetic mean of these 2n natural numbers, a1 up to a2n, taken to the power 2n. So this is precisely the property p of 2n. As we wanted to prove. So the conclusion is that both conditions A and B in the Cauchy principle of induction hold, and hence, by the Cauchy induction principle, we conclude that P of n holds for all n, right? And the way we have defined P of n was precisely that the Agm inequality holds for the number n, and so we have established the Agm inequality for all natural numbers. So this concludes the proof of the theorem, the Agm inequality. In the future, we will see some applications of this inequality to estimating limits of sequences or certain summations. However, this inequality also has many applications, for example, in financial mathematics or in computing. But for now, let us move on to the second topic of today's discussion, the extended real line. And symbolically, this is often represented as R together with the symbols plus and minus infinity. The aim is to introduce new piece of notation, namely, we're going to join two new symbols minus infinity and plus infinity to the set of real numbers R. So for this we have the following definition. We define the set R plus minus infinity to consist of all elements of the set R together with these two new symbols, minus infinity and plus infinity. So we already know the ordering on the real numbers. Now we can also extend the ordering on the real numbers to this larger set, so to all of R plus minus infinity, by declaring how the elements of the set of real numbers compare to these new elements. So we have to be able to say for any pair of elements in this extended set which one is greater than the other one, or whether they're equal. So for this, we declare the following inequalities. So we will say that minus infinity is less or equal than A is less or equal than plus infinity for every element A in the extended set R plus minus infinity. So in other words, if we look at the linear ordering on this extended set, we have that minus infinity is the smallest element with respect to the ordering, and plus infinity is the greatest element with respect to this ordering. So let's say this is the first part of the definition. We also define unbounded intervals. So we define the following unbounded intervals. Given any pair of real numbers A and B, so note that in this case A and B are actual real numbers as opposed to the elements of this extended set, so they can't include one of the infinity symbols, but for any pair A and B of real numbers, we define, first of all, we define the interval which is closed on the left, starting with A, and is open on the right, ending with plus infinity. By definition, this notation simply denotes the set of all real numbers x, such that A is less or equal than x. We also consider the two-sided open interval A plus infinity, which is going to consist of all real numbers x, for which A is strictly less than x. We also have an interval minus infinity B, where it's open on the left and closed on the right. So this means that this is the collection of all real numbers x, such that x is less or equal than B. And finally, we define the two-sided open interval minus infinity B, which by definition consists of all real numbers x, such that x is strictly less than B. So this is just new notation which is convenient to represent these sets for the sake of brevity. Now also, along with this, using the symbols plus and minus infinity in order to define the corresponding intervals, we define the meaning of the infimum and the supremum to this new context. So given any set S, a subset of the set of real numbers, non-empty, if S is not bounded from above, then we will say that the supremum of the set S is equal to plus infinity by definition, right? So remember that the supremum operator was only defined on those sets which are bounded from above, those sets of real numbers which are bounded from above. So here we're extending the meaning of that operator to a larger set of sets. So those sets which are not bounded, where we define the supremum in that case to be plus infinity. And similarly, if our set S is not bounded from below, then we declare the infimum of the set S to be the symbol minus infinity. Let's make a couple of remarks involving these new definitions. So, first of all, assume that S is any non-empty set of real numbers. Now, the symbols supremum of S and the infimum of S always make sense, regardless of whether the set S is bounded from above or below. So more specifically, if S is bounded from above, then the supremum of S is a real number by the completeness axiom for the reals. And if it's not bounded from above, then the supremum of S is necessarily plus infinity. Similarly, we have that if S is bounded from below, then the infimum of S is a real number by a corollary to the axiom of completeness. And if S is not bounded from below, then necessarily the infimum of S is equal to minus infinity. And moreover, we always have that the infimum of S is less or equal than the supremum of S, whether they are real numbers or minus infinity or plus infinity symbols. This is because of how we define the ordering on the extended real line. So by the definition of ordering on the extended real line are plus minus infinity. Now it's important to remark that there is nothing particularly deep about the introduction of these two new symbols, plus and minus infinity. The main purpose is to simplify the notation. For example, writing the interval minus infinity up to a is considerably shorter than writing the set of all x in R such that x is less than a. Similarly, writing that the infimum of the set S is minus infinity is shorter than writing the equivalent statement for every x real number. There exists some S, an element of S, such that S is less than x. So the symbols provide convenient notation to talk about various intervals, infimums, or in the future we'll see that they're also convenient to talk about limits of sequences and functions. An important point to remember in the future is that these two new symbols are not real numbers themselves. So they are elements of the extended real line, however they are not real numbers. They're just artificial endpoints that we attach to the real line to simplify certain expressions. This is important to keep in mind because in various theorems that we will state and prove in the future, or some of the ones which we have already proved, they apply to real numbers. You are not allowed to just you apply the same theorem with respect to one of the symbols. This is incorrect. Let's consider an example of an argument manipulating with these newly introduced symbols. So let A, B be two subsets of the set of real numbers, both non-empty. So A is not equal to the empty set and B is not equal to the empty set. We claim that then the supremum of the set of sums A plus B is equal to the supremum of the set A plus the supremum of the set B, where the set A plus B is by definition the set of all real numbers of the form A plus B, where the little a belongs to the set capital A and little b belongs to the set capital B. So this set A plus B is itself a set of real numbers, so it makes sense to talk about its supremum. Okay, so we would like to verify that this equality holds. So let X be an arbitrary element of the set A plus B, and by definition of A plus B we know that there exists a pair of real numbers, little a and little b, such that X is equal to A plus B. Okay. Now it follows that X, which is equal to A plus B, is less or equal supremum of A plus the supremum of B, because we know that the supremum of A and the supremum of B provide the corresponding upper bounds for an arbitrary element little a in the set capital A and an element B in the set capital B. As X is an arbitrary element of the set A plus B, we conclude that the supremum of A plus the supremum of B is an upper bound for the set A plus B. Hence, the supremum of A plus B, which by definition is the least upper bound for the set, must be less or equal than the sum of the suprema of A and B. This gives one side of the inequality, and so it remains to show the reverse inequality. So need to show that the supremum of A plus B is greater or equal than the supremum of A plus the supremum of B. As we have A is non-empty, this implies that the supremum of A is not equal to minus infinity, and similarly, as B is non-empty, it follows that the supremum of B is not equal to minus infinity. Note that if the supremum of A plus the supremum of B is equal to plus infinity, then at least one of them necessarily equal to plus infinity. Let's say the one corresponding to B. So we assume that the supremum of B is equal to plus infinity. So we pick some element A0 in A, and we have that the supremum of A plus B is necessarily greater or equal than the supremum of the set consisting of this single element A0 plus B, just because A0 is an element of A, so this is immediate from the definition, which is equal to A0 plus the supremum of B, which is equal to plus infinity. So the desired inequality holds in this case by our definition of the ordering on the extended real line. Otherwise, the sum of the supremum of A and the supremum of B is finite. In this case, we let epsilon be an arbitrary positive real number. Then by the definition of suprema, there exists some A, an element of the set capital A, and some b an element of the set capital B, so that we have that A is greater than the supremum of A minus epsilon over 2, and also B is greater than the supremum of the set B minus epsilon over 2. But then, if you look at the sum of these two elements, we get that A plus B is an element of the set capital A plus the set capital B. And so we have that the supremum of the set A plus B is greater or equal than A plus B, which is strictly greater than the supremum of the set capital A plus the supremum of the set capital B minus epsilon. And since we started with epsilon greater than 0 arbitrary real number, we conclude that the supremum of the set A plus B is greater or equal than the supremum of A plus the supremum of B. This concludes our discussion for today. Thank you for your attention and see you next time.